Hello and welcome to week 9 of the OpShin Pioneer program. So in this week the goal is to apply a bit the things we have learned throughout the past weeks and to build kind of a bit of a bigger, more realistic project, which will be a stablecoin dApp. So in this lecture I just want to kind of give an overview of what's the idea behind it and how we kind of can approach this. So what we will have in the end is both kind of the on-chain code, so the smart contracts, which will be written in OpShin. And then there will be also off-chain code, but this is actually something that was also covered in the Plutus Pioneer program, and the off-chain code is written in this kind of Next.js front-end framework. And since the code for this exists and it has nothing to do with the smart contract stuff, we will not be covering it again here. Okay, so yeah, let's just quickly understand how a stablecoin works, and then in the next lectures we will then dive into the code. So what kind of stablecoin are we building? So if you want a stablecoin, you need to somehow peg it to some fiat currency, say the US dollar. And what we're going to build is a so-called over-collateralized algorithmic stablecoin. And the way it works is that it maintains its peg through this kind of liquidation mechanism. So to say it simply, anyone who wants to mint a stablecoin has to lock more ADA than those coins are worth in the smart contract. And if then the value of the locked ADA ever drops too close to the value of what those minted coins are worth, then we would allow others to kind of burn coins and take the collateral, and this kind of keeps the peg. So for that we need 3 contracts. One is this collateral contract where you would lock your ADA. Then we need a minting policy that controls minting and burning of the stable coins. And then we also need kind of an oracle that somehow represents the current ADA to US dollar rate. So let's briefly discuss these different components. So first of all, the oracle. So the oracle in the end is just a UTXO at this oracle contract where the datum contains the current US dollar to ADA rate. And then when we first created, we also mint kind of an NFT using the same NFT minting policy we've seen in the previous week. And this NFT is just there to kind of uniquely identify which is the true oracle, so that not someone else can come and kind of create some fake data there. So then if the oracle, so the oracle needs to be updated, of course, regularly as the ADA to US dollar price changes. And to update it, basically we consume the UTXO that where the datum holds the current rate, and we replace it with the updated one. So what the oracle validator needs to check basically is that the input contains this NFT, the output will contain it again, and that the datum is somehow well formed, and that importantly the transaction is signed by the operator or the developer in this case, so that not anyone can just update it. So next let's talk about this collateral validator. So let's say we're a user and we want to mint some of these stable coins. So what we would do is we have some ADA and we lock them as a collateral in this collateral contract. And in this transaction, we also provide the Oracle UTXO as a reference so that the contract has access to the current price. And of course, we also provide the minting policy in this case as a reference script. And then this collateral provision transaction produces 2 outputs. One is at the UTXO at the user wallet, which contains then the minted stablecoins, and another UTXO at the collateral validator's address that holds the locked ADA. And the datum of this UTXO would store kind of the owner and which minting policy produced the coins and how many of it. So to make a concrete example, let's just say the oracle says that 1 ADA is worth $1, and the developer has chosen 150% as the minimum collateral. So if the user wants to mint, for example, 100 US dollar coins, then they must lock at least 150 ADA, which would be worth $150 in this case, as a collateral. And the collateral datum will record like the respective owner and amount. And the minting policy kind of enforces that this inequality, let's say, holds, so that the locked collateral value is at least 150 times the 150% times the minted value at the current Oracle rate. So then, let's say later, the user wants to again burn its stablecoin tokens and get back the ADA. So in this case, the transaction two validators would run in this transaction. So the first one is the collateral validator, because we're spending the collateral UTXO. And the second one is the minting policy, because we're burning stablecoins that belong to this policy. And actually the Oracle is not needed in this transaction, because we wrote into the collateral datum how many coins were minted against. So there's nothing we need to look up. And then basically the two scripts together, they would check that the burnt amount equals exactly this stablecoin amount we had recorded, and that the owner of the date that's written the datum has actually signed the transaction. And then, yeah, the user gets back their 150 ADA, and the 100 stablecoin tokens are burned. Then there's the other case, maybe more interestingly, where some user would liquidate someone else's position. And this is kind of the mechanism that in the end keeps the peg. So let's say some user 1 has minted 100 stablecoin tokens against 150 ADA at exactly this 150% minimum threshold. So even when the ADA price drops just a little bit, so now the 150 ADA is now worth only, let's say, $130, then we no longer have this threshold, so user 1 is under collateralized, since there's too little kind of backing up the 100 stable coins. And in this case, some user 2 can step in, and user 2 would kind of burn these, not these, like some other 100 stable coins that they have, let's say, and in turn can consume user 1's collateral UTXO. So this means that user 2 now receives all of user 1's locked data, which, even though the price dropped a little bit because we have this 150% collateralization, there's still some difference that basically the user would keep and profit from, and user 1 loses this. So this is exactly the mechanism that keeps the peg in the end. So if the position drifts, if ADA, let's say, drops in value, there's a strong incentive for someone else to consume this collateral and burn the coins, and this way the coins don't lose in value, let's say. So kind of these two forces push the system back to the stable true value state. Okay, so now we basically covered at a high level how this decentralized app would work. So we talked about how the Oracle is implemented, that there's this collateral validator, and there's the minting policy. And yeah, this together creates this kind of incentive to liquidate and thereby keeping the peg of the coin. And then in the next lectures, we will kind of dive into each of these components more concretely in terms of looking at the actual contract code. And yeah, I just want to emphasize again that we will not cover the front end here, because the front end is the same whether you use Plutus or OpShin or any other smart contract language. And if you want to actually see how this works, there's the lecture 2 of week 9 in the Plutus Pioneer program that kind of walks you through how to set up and use the front end. And we will continue with lecture 3 of this week, where we have a look at the on-chain Oracle code. See you.